Well, you all stopped talking simultaneously, so I guess that's the signal that we're supposed to start. I'd like to welcome you to the first lecture in our 9th annual lecture series. And some of you know that we used to start this series in January, and this year we learned our hard lesson not to try to compete with the weather. And boy, I'll tell you, yesterday, in the midst of that snow flurry, I was wondering if we had moved them back far enough, but I'm certainly glad that you did not have to climb over glaciers to get here today. If you have not yet seen the rest of the listing for our lectures, which will occur April, May, and June, there are flyers out in the lobby, and please pick one up and pin it on your refrigerator so that you know when to come and see us again. Now, we do hope that you had a chance to browse our shop in the lobby. There's a charming small book about Wes and the Buchele family titled Just Call Us Lucky. Wes and his brother Luther, his twin brother Luther, wrote that book. And in addition to that, there are more detailed papers on Dr. Buchele's technological history. Now tonight you're really going to hear the capsule summary of Wes's accomplishments and inventions. And if you want the bigger, more expanded, and more colorful story, you might pick up one of those papers out in the lobby. The shop will remain open after the lecture if you'd like to browse just a little bit more. Now, I think someone probably snagged you as you came in to sign up for the door prize drawing, and we are going to draw for 2 prizes at the end, so if you stick it out all the way through to the end, someone might get a great prize. And one of them actually will be one of Wes's little books. Now, I do know that you'll enjoy tonight's program. There are hundreds of local history stories as interesting as the one that you will hear tonight, but putting them together takes time and resources. Memberships in Ames Historical Society provide those resources. If you are not a member, we hope that you'll consider becoming a member to ensure the preservation of our collective past. All these great stories. There are membership forms in the lobby. And we sincerely thank those in the audience who are already members. Your support means absolutely everything to us. Now this year, 2014, we are celebrating the sesquicentennial, the 150th anniversary of the founding of Ames. Committees are hard at work on a number of special events and programs, so as the year goes on, be sure to watch for dates and schedules, and do feel invited to attend all of the exciting things that will be going on. Now, there is a website for the Ames Sesquicentennial, ames150.org, so you can look there for information, and as events develop, they will be added to the website, so it will be changing as time goes on. I think we're about ready to start, but before I introduce Dr. Buchele, I wanted to give you just a short overview of agricultural engineering at Iowa State. Push this on. In 1905, J. Brownlee Davidson organized the first professional agricultural engineering program in the whole world at the school that would become Iowa State University. Davidson had gotten his degree in mechanical engineering from the University of Nebraska and was hired by Dean Charles Curtis in Iowa State's College of Agriculture to teach agronomy. When farmers kept coming to the engineering college for advice about problems with their one-cycle water pump engines, Marston referred them to Curtis. Since this was an important area of interest to Iowa farmers, Curtis oversaw the development of a program of what was then called farm mechanics. Davidson saw clearly the need to prepare student engineers to apply technology to solve agricultural problems. And the department has become a leader in providing engineering solutions to agricultural challenges in the United States and around the world. In 2004, the I.S.U. Department of Industrial Education and Technology merged with Agricultural Engineering to become the current Department of Agricultural and Biosystems Engineering. ABE is now the focus for technology education at Iowa State. The department's original mission was to mechanize agriculture, That mission has evolved to encompass a global view of the entire food production system, the wise management of natural resources in the production, processing, storage, handling, and use of food, fiber, and other biological products. Current research efforts include agricultural water quality and management, engineering for economically and environmentally sound animal production systems, grain handling and food processing, agricultural machine design and automated controls, precision farming systems, agricultural safety, seed conditioning and processing, and soil tillage and management systems. You may have read just within the last couple of weeks in the Ames Tribune that Iowa State's Agricultural Engineering Department was recognized nationally for its accomplishments, rating number 4 in the whole nation among similar programs. Interestingly, since 1905, the department was administered through the College of Agriculture, and it remains that way today, despite its strong engineering emphasis. Now, when tonight's speaker enrolled in graduate school at Iowa State in 1951, J.B. Davidson was teaching his last class, a graduate seminar. And Wes had the privilege of being in it. Imagine that. 1905, Davidson started the department. And here he still was in 1951, teaching. So, Wes Buchele represents the last living link to the very beginnings of agricultural engineering at Iowa State. So, here's the introduction. I'm going to introduce you. I'm going to talk at you just a little bit more. Okay. So when Dr. Buchele and I started working together on tonight's presentation, he gave me a copy of his professional vita. It didn't take more than a glance at its 11 pages to know that he has been able to accomplish a great deal in his life as a teacher, researcher, and inventor. Wes grew up on a dairy, grain, and livestock farm near Cedar Vale, Kansas. He and his twin brother, Luther, were the youngest of the 7 Buchele children, all boys. He was a natural tinkerer, and working on the farm with his family inspired him to use his talents to develop ways to make farming easier, safer, and more productive. After sweating through many harvests, he especially wanted to do away with the labor-intensive small square bale. Encouraged by his mother, he got his first degree in 1943 in agricultural engineering from Kansas State. After his Army service ended in 1946, he worked for 2 years at John Deere, then pursued his master's in ag engineering at the University of Arkansas, finishing in 1951 and earning his first patent for the hydrostatic torque meter, a device that measured an airplane fuel pump's efficiency and state of wear. In 1951, he came to Iowa State to start work on his PhD, this time a double major in agricultural engineering and soil physics that emphasized both machines and their effect on Iowa's greatest natural resource, its rich black topsoil. He worked under the very creative Professor E.V. Collins, a man with 36 patents to his name. Collins challenged Wes to improve the efficiency of threshing red clover, which he did, the first of his inventions at Iowa State. Research for his second PhD major, soil physics, explored ridge-till planting of corn that reduces soil erosion. Wes finished his PhD in 1954 and worked in Ames for several years before leaving Iowa State to teach at Michigan State from 1956 to 63. He returned to I.S.U's Agricultural Engineering Department in 1963, where he finally got started on his ideas for a new type of baler. In 1966, the large round baler was shown for the first time at Living History Farms. Wes is grateful to his bosses at Iowa State, who gave him free rein to pursue a number of ideas in research and teaching. In 1972, he introduced the first ag safety course in the United States. By the time he retired in 1989, he had 23 patents to his name and had developed a number of other inventions that didn't go through the patent process. So that 11-page vita shows service in the Army Reserves, travel around the world to advise agricultural projects, books and articles published, committees, conferences and associations contributed to, guest lectureships and consulting, and numerous awards, including in 2003, the Henry A. Wallace Award for significant contributions to agriculture. And in 2010, he was inducted into the Product Design and Development Design Engineer Hall of Fame that also includes Thomas Edison and Henry Ford. Wes's goal in retirement is to have a few more of his inventions in wide use, and also to have Ames known as the home of the round baler and rotary thresher. So now I'm going to get out of the way and let Wes talk about his inventions.
Thank you, Kathy, for those kind words. And I have noted here on the slides that I have 23 patents. One of the things that I'd like to accomplish today is that those 23 patents will have a home here in Ames, Iowa. And that is one of my jobs today, is to have you accept them here as the home of the patents. As Kathy has said, my major professor was E.B. Collins, who was a resident of Ames, and he had 23 patents. And I never got that many, Kathy. He had 36. Oh, I was wrong. That's the Betsy. I'm glad we didn't argue about that. Okay. Can you hear me? No. Is everything okay? No. Yeah, well, I'm looking out over a light. I can just barely see the audience. So I'm just going to tell you my story. That's what Kathy said. This is Wes Buchele's story. I'm 94 years old. This will probably be my last lecture. And I had the thrill of sitting in on J.B. Davidson's last class at Iowa State University, where he taught a graduate student seminar. And 1931, the fall semester was his last class that he taught. And I attended that class. And so I'm a living representative of J.B. Davidson. After the war, I came to Ames, to Iowa State, after I visited my wife's home at Minneapolis, Kansas, and my own home at Cedarville, Kansas, and visited the other brothers. I had 6 brothers. I'm the 7th son. And I then went out to search for a job after getting out of the Army. And I found that most of the farm machinery companies had already hired their engineers that came out of the Army, because I didn't come out of the Army until 1946, in the summer of 46. But when I went to Waterloo, I found friends. I had worked there as a summer of 1941 or 1942, I can't remember. And because I had worked there before the war, they hired me, and I had a wonderful time there learning engineering at John Deere. I became a professional engineer. After spending 2 years there, I decided I would like to continue my education, and I'm not really education. But I want to talk about John Deere just a little bit, in that they were putting into production, the Model R tractor. Now, this was the largest tractor that was being built at that time. And so they gave me jobs to work on it there, and as I rotated through the engineering department, from research to the engineering shop, to new design, to development. And each one of those I was given jobs to work on the Model R tractor. And this is the Model R tractor. It was the biggest tractor that was being built at that time. It was 48 horsepower. And it had a starting engine, a 4-cylinder starting engine to start as a 2-cylinder tractor. And I was given the job of making up that 4-cylinder tractor with a flywheel on the tractor. And I was going to show you the flywheel here in just a second. The flywheel is here, but it's now covered. So there's a 4-cylinder starting motor behind here that would start that and started. And then they had me work on the loading system, the tractor, and on the full throttle of the tractor in the new design department. And then they decided to have me work in the development department, and I worked on various projects there to improve the tractor. Well, I had been in the Army for 3.5 years total, and I enjoyed working with young people. And I decided to exercise my GI Bill of Rights. So I went down I found out the University of Arkansas had a research contract to investigate cotton mechanization. Now, cotton mechanization is a great crop, and it's like corn here. It's a major crop. And you should all be happy with that, because before cotton became a fabric, or general use fabric, people wore wool in the summertime, and that's itchy stuff. So I went down there and worked on that, and then I became, I worked on a master's degree, and I developed a hydrostatic torque meter, which I did invent. Go to the next slide. And so this is a hydrostatic torque meter. I organized with a couple of men, and we put that in production. And it's sold to the Farm Machinery Company, and it's sold to the American airplane companies, as well as the other airplane companies around the world. The test that they ran with it in the Air Force was to run a test provided by the government to test the pump that pumped jet fuel to the jet engines of the airplane. And it had to develop a certain pressure and a certain oil flow to pass the test. And it couldn't be tested in a building that was equipped with electricity. So this was in competition with the strain gauges that were being developed at that time, but they had electricity. There was strain gauge torque meters too. So about 35 different aircraft companies bought my rotary torque hydrostatic torque meter. Next slide. Then I went I then moved from Iowa State, from University of Arkansas, and I came into Iowa State University in the fall of 1931. I went into my major professor's office, E.B. Collins, to introduce myself, and in 10 minutes he had assigned me the job of designing a new threshing machine. The threshing machine we had been using was developed 164 years before, and consisted of a cylinder and a straw rack. Somebody would shell out the grain, and then it was the straw auger's job to separate the grain from the straw. So I eliminated that straw rack, and I created a system of threshing and separating system that's all in one bed, and here it is on the screen, and this is the cone thresher that I built, and this is fed at the small end here. There's a rotor in here, a rotor right here that rotates in a fan there, and then it's enclosed in a screen, and that the grain is separated out, and then it's thrown out and goes through the screen here, and the straw travels down the screen and inside of the screen, and the straw is eliminated here. This particular machine, go ahead, next slide. I had a graduate student at Michigan State that Bill Lauder, and he built this rotary cone, and then, next slide, and then he run tests, and here we're threshing the crop, and then after we threshed it, we separated the grain from the straw to determine the efficiency of the threshing system. It was 99% efficient on the first test and 76% efficient on separation. So it wasn't a big job to bring that around to the point it would be commercialized. The first job that I saw when I came to Iowa State was that they had the Rosenthal total corn harvester. Back in 1950, they were suggesting, Rosenthal brothers were suggesting that we harvest the total crop. And this meant that we're going to save those nutrients, because half the corn crop nutrients are in the stalk and the husk and the cobs, and the other half is in the grain. And so the farmers were 50% efficient in harvesting the nutrients of the crop. And so, next slide. And so the Rosenthal brothers up in Minnesota had built this machine. It picked the ear, it elevated the ear corn into the wagon, it elevated the dry husks and stalks into another wagon. And here is the Rosenthal machine, and here is this husks going this direction, stalk, and over here is the ear corn going in the wagon. Next slide. And J.I. Case took up the idea, and they built a total corn harvester in 1950. And here it is being tested. They're out here where the alumni office is now. And but it was not accepted because it was before its time. Farmers were interested in harvesting grain. And they still are interested in harvesting grain. But I have gone to another total corn harvesting project, which I'll talk about in just a moment. Next slide. In this Rosenthal, what we did was they cut off the stalk. The stalk was carried through and thrown into the wagon, and then the ear corn was snapped off here, and with the snapping bars, and carried into the other wagon. Next slide. And here it is in the field, delivering the stalks, the grain here, and the stalks, the silage in here, although it wasn't silage, it was dry stalks. Next slide. Okay, we have now the next slide I'm going to talk about is the rotary thresher. I moved to Michigan State, as I stated, and we tested it up there. Lloyd Johnson from the International Rice Research Institute was traveling the world, and he was trying to find some kind of a threshing system, a tillage system that the Filipino 1 hectare rice farmers could use. And I showed him my rotary threshing cylinder, and I showed him my tandem tractors. Next slide. And so what we show you here is the cone threshers that he designed up from in the Philippines. And here is the tandem tractor that I showed him when he was here. So he used both of my ideas. But the problem was he made them too large for a 1 hectare farmer. And as a result, they were never used. And then eventually, not eventually, but the next year, he operated a assembly of engineers in Southeast Asia and to have a conference on the engineering aspects of rice production. And he invited me to come there and do the conference, and I got to see this equipment and attend the conference. And so then they sent him to South America and to start an international research organization in Colombia, South America. I don't know exactly what they worked on down there, but Emir Khan, a Pakistani engineer, replaced him. And what happened, what he had built was this little threshing machine here, and that was exactly what they needed in the Philippines. And they developed this up, and they put it in production, and that went around the world in the third world countries, operating a 1-cylinder engine and threshing the rice crop wherever they go. And it was quite successful. The grain, we fed it in here, the grain came out the bottom here and was collected here, and the straw went out the other end. And so this was the system that Emir Khan built, and then he received a $25,000 prize from the King of Sweden for developing this process. Next slide. My wife and I talked in China in 1983. And when I went out and visited the communes, I saw a cone thresher of the communes. They had read my patent because Emir Khan, I don't think, ever read the patent, because he built a cone, whereas this is a cylinder, whereas this is a cone. And it has an outline here and a top outline there, fed tangentially in here. The straw goes completely in and out, and the grain is caught here. And this was a very successful measurement, which from Emir Khan's work. The American modern machinery industry used Emir Khan's ideas for building a threshing machine, building a combine, and that is what is being used on the farms today. But was issued a basic patent on that particular thing, and the basic patent consists of 2 patents. A patent, an apparatus patent, and a method patent. They patented the method patent first, and the apparatus patent said, and I was just a grad student, and I had to pay for all that patent stuff myself. The I.S.U. State University had the rule that if a grad student wanted to patent their own patents, they could, and then they could manage the patents. That didn't turn out to be a very good idea because I got real busy. I didn't manage the patents. And the first time I saw my patents being used by commercial industry in the United States was in 1975. My patents had 1 more year to run. When I was in China, with my wife and I saw a rotary threshing system, was made out of brick and concrete. That was amazing to me. And this was at CN, and that's where the terracotta soldiers were. And so I like to see the terracotta soldiers, but this was quite amazing to me. Next slide. And here is the bottom of the grate, where the grain comes out from this threshing system, and this is part of the cylinder. Next slide. In the United States, we are building combines with the rotary combines, and this is the rotor out of an international combine. And it's fed here at this end, auger lights the crop in, and sliced back in here. The grain goes out the screen here, and the straw goes out the far end there. They use here in a cone rather than a cylinder, but I was saying a directional screw here that carries the straw out of the combine, and the grain comes down. Oh, the grain comes down here. The directional is like a screw, and it goes around and around and around, and as it goes around and around, the straw travels this way. Of course, the grain travels that way through, but the grain goes through the sieve down here, and the grain is caught down below. What goes is thrown through there, and they get the separation of the straw from the grain and the malt other than grain, and then they separate that by air on the sieve. Next slide. Now, after I graduated with a PhD, I then was hired by the U.S. Department of Agriculture to work on ridge tail, and I'm going to talk about ridge tail in a little bit. I want to talk about tandem tractors because that was I did that work in the summertime and in the wintertime, and so I developed a tandem tractor. Next slide. And here is a tandem tractor, and there's my major professor operating the tractor. And he liked that so well that he built his own tandem tractor. And what we have here is, next slide, is that by putting the tractors together, we eliminated the front wheels. And each set of front wheels took the force of one plow to have the wheels rotate on the ground so you could drive. And so what tandem addition is 2 plus 2 equals 6. And then besides that, we have the rear tractor in second gear, and the first tractor in third gear, and the whole thing run faster than the tractors would individually. And I call it the front tractor the John the Baptist tractor because they prepared the way for the second tractors by giving it a compacted track to track on. And it worked really successfully. What's interesting is that E.B. Collins, after he made his tractor, he had it shipped to Detroit with my tractor that I had built, and had C.P. Ritchie, who was a grad student at Iowa State University, to test them. And he tested and wrote a report, a very glowing report on them. And the farm machinery companies started to work. E.B. Collins decided that he would like to go around and educate the tractor industry on the use of four-wheel drives. And so he organized a trip, and went around to each one of the farm machinery industries. And he went into the chief engineer's office, and after the greetings and so forth, he would tell them, I would like to talk to you about building four-wheel drives. Oh, we should go out to the rich department. the research department. They went out to the research department, and there they were building a four-wheel drive tractor. And he did that on every farm machinery company was building four-wheel drive tractors. And because the greater efficiency, 50% more work, 50% fuel saving, 100% saving, in labor. So here we are with a new system. Now I built that in 1954. It was 1963 before they started to market those tractors. It took them 9 years of testing and designing, testing, and so forth to get a field-worthy tractor, and they came on the market in a whole bunch in 1963. Next slide. Here is a Volvo tractor with a set of front wheels. I call that a semi-town tractor, and the driver had to drive the front tractor there. And his grain drill was located way back there, and he couldn't see what he was doing. So the tandem tractor was operated from the back tractor, and it was successful. But it's not being used now. I think it kind of went out about 1975, something like that, as the new four-wheel drive tractors came in. Next slide. The third effort for the harvesting of the crop residue. Next slide. What we did is we cut off the stalk, we snapped off the ear, we shelled the kernels off the cob, and then we chopped the stalk and threw those in the wagon as high moisture silage. And this was built by Tom Heitsusen with Dr. Steve Marley as his major professor. And here is the sweetest machine you'll ever see. And he divided the machine and set the stalk chopper out, stalk cut-off system out front, and set in the middle of here a snapping system for snapping off the ear, carrying, elevating it, and shelling it here, and then the grain would be elevated here, and the stalks, silage, high moisture corn would be stalks and leaves would be elevated there. Next slide. And so here we have a sweet little machine. It has two-row machine, and it was a jewel. Unfortunately, here's the next slide. Let's see how it worked. Cut off the stalk here, snap off the ear here, shell the ear to get grain here in the sheller, and then elevate that in the wagon, and then chop the stalk here, and roll that up in the wagon. And that system required, this slide, a double box wagon. Did you ever see a double box wagon? Here is the double box wagon back here, and the grain went in the box here, and because it could be smaller because the grain is not as large as the stalks and the husk and so forth. And so here, this is the high moisture stalks went into the silo. Well, that system sounds real good, except that the farmers are interested in harvesting corn. They're not interested in harvesting stalks at that time, so it was unsuccessful. Next slide. Well, I wrote a paper on that, and what it shows is that at that time we were getting 6,000 pounds of stalks off the field, husks and so forth. And so I divided that up, and I showed you should leave 2,000 pounds of stalks in the field to protect the soil, and then we used the rest of it for heating the farmhouse, for feeding the livestock, and for whatever else I had there. And then there was 3,000 pounds left to send off to DuPont to make ethanol. But Dumont was not here at that time. So anyhow, that was the third try. Now we're going into the fourth try of harvesting corn stalks, and it may be successful and it may not be successful. That is to be written in the future. But they're going to give it a 20 million ton try out here between Ames and Nevada. They're building a plant to do that job of making ethanol.
You were just ahead of your time.
Well, I'm ahead of the time all the time. That's where I intended to be, was ahead of the times. Thank you very much. Okay, now, as a researcher, I found that you were no smarter than your instruments. And you had to build your own instruments to do the research. And one thing I needed was an undisturbed core sampler, which would pull a sample of soil exactly like it was in the soil so we could look at it. And so I built this slide. I built a soil sampler. And there you could drill the soil to 16 inches. That would get that down below the topsoil and the compression of the soil of the mile of ice that actually was on the soil here, where we're sitting here today, the pressure that compacted the soil. And then we cut the column into 8 parts, we dried it, we weighed the column, and then with that we knew the volume because we cut it, had rings that were a known height, and from that we could plot a graph of the various moisture content, the bulk content, the moisture content, the bulk density, the eggs, the worms in it, whatever you wanted to know about the soil. You had an exact column of the soil. So now how did it work? Next slide. Here is my some students here digging a sample. This is a pattern drawing of the machine. It has interior tube here that went down, and it trimmed this column of soil that had been cut out by those augers there. And the soil diameter of the soil was shorter, less than the diameter of the tube, so the soil would go up the tube, would stay stationary as the tube was lowered into the ground. It was a balancing act. I'll tell you. And so here we are, we dug into the ground, we pull the tube out, the tube is laid down in a half tube, and with a knife here, we cut it off, and we cut the soil off here, and then at the next junction of the ring, we cut the slide again. That gives a known height volume of soil, and then we weigh that, and we know what the volume is. From there we can calculate the bulk density of the soil. You can calculate the moisture content, and you can look for worms and eggs and seed and stuff like that. Next slide. Well, the soil loss was a great concern to the United States and certainly to Iowa. We have the most erosive soil in the country, and we have the most erosive rain in the country, all paired together. So when I arrived here in 1950, it was 25 years after the Soil Conservation Service was established. And so the next slide. They were published in the Des Moines paper that there was a gully washing of rain that washed off 50 tons of soil per acre. And next slide, and here is the Secretaries of Agriculture, and Bennett was the Secretary of Agriculture. And he also started the Soil Conservation Service. And so here is 1 billion tons of soil lost per year. He said it was about 2.5, 3, and then on up and on up and up and up. Anyway, then this is going up in there, and then it has come down from no-till and from ridge-till, which we developed here. No-till was developed in Ohio, and we are now having less soil loss than we used to do, although we seem to be having a lot more floods, and we're going to have to figure that out. Here is a gully that washed in a side hill that a farmer was farming. But he was farming this land, and the water washed it away. Also, here is a road highway, and a dust storm blowing across the highway. The highway department, when they needed topsoil, they went out and cleaned out their ditches. They didn't pay the farmer a cent for that. Next slide. Here's the factors that led to ridge-till. Water erosion was excessive. Thank you. The gullies formed in the fields. Wind erosion was excessive. Roadside ditches were filling with soil. The soil compaction was increasing. E.B. Collins invented the ridge-till, and he asked me to join the ridge-till research committee. And so I gave up my work on the rotary threshing cylinder to work on the ridge-till as my PhD thesis. Next slide. So we conducted research. And nowadays, there's about 4 million acres in Iowa and Minnesota that actually use ridge-till. Most of the other farmers use no-till, and those are the two systems that are conserving our soil today. What the procedure is on ridge-till is that you have a ridge, and you probably form that from the regular planted corn the first year, and then you spray the ridge for weed control. The first cultivation you borrow off, come in and borrow off the soil, and then the second cultivation you hip up the ridge, throw it up, and that forms the ridge for the following year to plant the next spring. And then we spray for corn control, and then harvest the crop. And that's the sequence of growing there. Next slide. Here is ridge planted corn. These furrows are, ridges are about 8 inches, 6 to 8 inches higher than the so that fills the water during the rain, and the water filtrates in the ground, or it doesn't do that. This is contoured to the waterway and would be lost in the waterway. But we've known to get this when you keep water on the soil, because rains are not constant. And so it will go in, water will infiltrate in between the showers. And so, next slide. Here is after the corn is matured and has been combined, this is the bullywurger stalk. It has been beat up and chewed up by the snapping rolls, and you see that the crop residue is located in the furrow and on the ridge. Next slide. And here we are, there's a seed planted here in the following spring. The soil has been thrown out, and it would be thrown here and into the furrow and so forth. And here this continues each year, and can be used for soybeans, and you could be farming this ground for 1,000 years with no till, with ridge-till. We cooperated with the U.S. Department of Agriculture in rainmaking, and when they run their rainmaking, they run the rows up and down the hill. And I asked Bill Molauer, why do you run the rows up and down when the ridge hill is supposed to be on the contour? He said, well, we have to get some data. And if we had it on the contour, we wouldn't get any runoff data. So, okay. And so here is tests that they run on this to determine the soil saving value of the ridge hill. And so here we are on a 6%, maybe 9% slope, and that would be on conventional farming. And you see that we're getting a lot of washing, and then next slide. And this is water that was caught, and we were testing no-till, ridge-till, plow plant, and conventional farming. And so here we are, and we caught the soil in the jugs here, boiled off the water, and then measured the amount of soil that was caught from the slot that was eroded off the slot to give us a graph. Engineers just love graphs. And so here it is, conventional farming, 20 tons at 3% slope and 40 tons per acre at 9% slope. That's no news to you. Erosion goes up as you have higher and higher slopes. But here is your till plant, and I've been over Nebraska, and they had 10 tons lost on 3% slope, but 20 tons on 9% slope. Here is ridge till, and here is about 5 tons per acre at 3%, 5 tons, 6 tons per acre for 6% slope, and 4 tons per acre at 9% slope. And so here was a system that we could save the soil, keep it in Iowa where it belongs, other than sending it down the Mississippi River. Unfortunately, no-till came along and has taken over some of the crops that were the farmers who had converted their machinery to ridge-till and converted back to no-till. Next slide. Here is the state of farming when I came to Iowa. That land had been plowed. It had been disked. It had been disked again. It had been harrowed. It had been harrowed again. What it needed to do was to plow it again, but the farmers would plant corn in it and think he had a good job. Next slide. My brother Paul took this picture. It's an amazing picture. And here's a wheat field in southeastern Kansas. The farmer harvested the wheat. He plowed the ground. He then disked the ground, and he disked the ground going this way. And then he disked the ground going this way. And you can even see the disc marks in the tractor tracks that have made by the tractor as he worked in this field. Along came a flood, and it washed off all the loose soil on this field. And here we have the tractor tracks that were made compacted as the tractor pulled the disc in the field, pulled the disc going this in the field. And the farmers don't understand that when they run a tractor across the field, you make tracks. And those tracks are there for quite a while. And of course, if you plow up the tracks. But if you don't plow, you don't plow up the tracks. Next slide. One of the next things I wanted to do was to create a formed ridge. And I made a ridge where the south side of the ridge, this is out here west of town, and it was perpendicular, the side of this ridge was perpendicular to the sun. It came down here at a 90-degree angle. And then the north side of this was a steep angle. And that formed a ridge, produced 4 to 40 bushel per acre also corn. Then the ridge, where we plant on the ridge, the top of the ridge. And the reason for that was that we could warm up this ridge, get the plant growing when it's warm, when the ridge is warmed up by perpendicular sun hitting the side of the ridge. And the grad student that did this, he had the planter here in front, and the ridge maker beside it, made the ridge over the seed, and then he tried it as the artist researcher would do the other way, next slide. And here we are, with making the ridges in front, and then planting in the ridges behind. And that was, we're not using that. Come back another a century or two, and we will be using it. I saw this being used down in Peru, out in the hills of the Andes, and I think we'll do it again. This shows a field of rich tilled corn. It shows the collection of the threshing of furrows. This shows the collection of snow in the furrows, and then when it dried up and warmed up, then it was ready for planting. Next slide. I went out in the field on a tractor when it was raining, and I took pictures of my ridge planted corn. And you can see the various corn located here. This is a tractor track furrow. This is a tractor track furrow, and the middle track here had no track in it. What you see is a traffic impart reduces the amount of infiltration of water into the soil. And so this water, if it stays here, it will infiltrate eventually, or if more water rain comes, it will flow to the grassed waterway and go down the Mississippi River. So this is shows the value of the ridges for impounding water temporarily during rain. Next slide. Here is planting corn out into western Iowa in the Lust Hills. Next slide. Here is planted corn ridge. You see the soil has been tossed aside onto the crop residue, and it ties it down. Next slide. Here is the corn. You see the corn is growing right here beside those old stalks, right there, the old roots. And it does very well. Next slide. And when I was doing the research, we did hill planting. I imagine that there's some farmers here that have hill planted their corn. And the reason for that was that if you put 3 seeds together, they might have the emerging force to break the crust. Well, when we went to Ridge Hill, we found out we didn't have a very strong crust, and so we planted on 6-inch centers, and we have our rich corn here, 6 inches apart instead of 40 inches apart as we were doing then. Next slide. Now, in Iowa, we have buffalo waters. And in buffalo waters, they're in ponds. And so I have here one of my plots going through a buffalo water. And the ridges planted on this side of the plot, buffalo water, grew corn. And the buffalo water, the ones that I planted, grew weeds because the corn drowned in that pond. And so it has the ability to keep the corn growing by reducing flooding, and then also because there's ridges located north and south here if it kept water flowing in from the west and flowing from the east into the Buffalo Wallow and reduced the height of water in the impoundment. Next slide. The farmers, when I talk to them, well, they grow 80 bushel corn and have a 10 ton per acre soil loss. They don't know how to understand, how to match those together. They know one is high and the other is low. So I developed what I call a farming system ratio. It's a dimensionless-free number. So you are dividing bushels of corn by bushels of soil, or tons of soil by tons of crop, and so forth. And it's a number that indicates the units of soil sacrificed per unit of grain produced. The Buchele farmer system ratio is soil loss divided by grain yield. Now, what I need to show, and I need a very important statement here, is that a prudent society will minimize the ratio by selecting an appropriate system of crop production that has a low Buchele soil loss ratio. And here is some soil loss ratios. If you had a 30 ton per acre soil loss here, the corn and 180 bushel per acre would have a 5.4 pounds of soil lost per pound of grain. Here is soybeans, 50 bushel acre, 10 pounds of soil loss per pound of soybeans. This is because there's less weight, so less yield from soybeans, and so you have a higher Buchele farming ratio. Here is ridge till down here, and it has 1/4 of a ton per acre loss, and here it is a ratio of 0.046, and for soybeans it would be 0.9. So you see that this would be a good system for farmers to adopt to understand what is happening to the fields. Next slide. Okay, we have the farmers have a problem. They have to have two heads. They have to have a soybean head and they have to have a corn head. Why not have a single universal head? So one of my grad students went to work and he produced a universal combine head. This slide. Okay, sorry. In this particular, we bought the nest of corn, we spray the corn for weed control, and then we harvest with the universal header. Next slide. Now here is a universal header. It's set up for 15 inch corn, the spacing of 15 inches. It has a mat rule. What happens here is, as you go down through the field, you cut the corn off, and then you can elevate the corn, and there's a snapping hole here at the top of the feeder housing, and you snap off the ear, and that fence goes down into the auger underneath, and then corn is elevated and shelled. The stalk of corn continues through the snapping rolls and runs into this auger that augers all of the stalks and leaves and so forth to the side, and it's windrows by the side of the compound. And that was really cute. It really was neat. And you got your corn so you could make silage out of it. You got your grain, and you raised a higher crop because you can get more yield out of 15-inch corn than you can out of 30-inch corn or 40-inch corn that we used to raise. He tried a chain reel, and that worked okay. Next slide. And so here is, we're planting now 15-inch rows, and corn increases the yield when you go from 30 inches to 15 inches, and the soybeans don't. But here we are increasing yield because you have 15 inches using a universal header. Now we go to the large round baler. You've been waiting for that. The large round baler was invented by Wesley Buchele and Virgil Haverdine. Virgil Haverdine came into my office in 1965 in the spring. He was looking for John Deere, and he came up to Ames to talk about graduate work. He came into my office and he sat down with a very worried look on his face. He said, "Will you suggest a graduate student problem for me?" I said, "Yes, let's build a large round baler." And he was aghast. And he said, "Why do we need a large round baler?" And I said, "Well, I don't know of any farmer or any farm kid that would like to throw around 70-pound bales of hay." When I was 16 years old, here I am in Kansas, not with this baler, but with a baler, John Deere baler, and I run a 4-man crew and a boy baling hay. I was the boy. As I pitched hay in hot weather, it was 115 degrees in the shade, and there was no shade out in the field. And I made an oath, I took an oath, that I would eliminate the little square bale because of the hard work it was on the farmer. And so 30 years later, I talked to Virgil Haverdine about making a large round baler. And he accepted the idea, and what I found was that there were 7 patents issued to American farmers to make large round bales. But they never made a round bale. They just made the baler at various stages. Some of them they built the baler, some of them they did not build the baler. Around the world, there were 7 people that did that. We at Iowa State were the first people in the world to actually make a large round bale of hay. And so then we did this, and Virgil Haverdine went to work. He drove the baler. He had to, this line. Here is his baler, and but he had to develop it. Next slide. Here is these little cones here are, oh, here's the wrong thing. These cones here are in the elevating system in which we can move the wheel out over the back to unload it. Here's the patent drawings there, you see. Next slide. Here we are in the system, in the business of showing how to unload the baler. Next slide. Here we are making hay. Now the hay has been windrowed. Next slide. Here is we're unloading the baler. We're unloading the baler over the back. Next slide. Hey. And there is the round balers from the commercial baler, and it has a plastic sheet on it with a twine holding it on, and that's a good way of doing it. Here is a plastic seat unwrapper. That wrapper wraps the bale in plastic. Next slide. And here is the field, and it shows the distribution at one time. Here's the distribution of square bales, with small square bales. And here's the distribution of large round bales. Next slide. Here is a tractor carrying a bale of hay with a front-end loader. And next slide. Here is a tractor carrying a bale of hay with the rear spikes, and here is the baler, has the bale up in front, so he's carrying 2 bales, and here is the gravel fork that keeps the bale on the front end loader. Oftentimes, actually, like I said, oftentimes farmers don't have this gravel fork, and they raise this up, and if they don't have a cap on it, they drop it on themselves, and they will never walk again. And there's a lot of farmers that have failed to watch the height of the bottom of that, or have a gravel fork, or have the front end loader. So it's been a very tragic introduction to farming here. Next slide. The gravel fork is shown handling the bales here and here. Next slide. The Iowa legislature cooperated with American Iowa farmers and said you can haul 2 bales, 5-foot wide bales, on a wagon down the highway. And so here's a 10-foot load of hay bales ready to go down the highway. Next slide. Here is feeding a large round bale of hay on a sloping ground. And so you see is let go of the bale. Here it is rolling down the hill and unrolling itself so it distributes the hay along the side of the hill. Sometimes people have rolled these down the hills and they've taken out a car or a truck and got a pipe on it. It can happen. Next slide. Here is the bales being set up for a weather test, and we baled this at 35% moisture, and we baled hay, the small square bales at 35% moisture. Next slide. Here we are, here the bale. Next slide. Here is the test. The 35% moisture, yes, it molded. Here is our weather damage up on top. Here is the bale, large round bale of hay. This is 35% moisture. The hay leaves were bright and green and on the stems. And it was a way to go. What I propose is that after we harvest the hay and dry it, to make it worth more money, we should then compact it. Next slide. Okay. Here is baling stalks on a round baler, and they will eventually go to DuPont to make ethanol. This was taken about 20 years ago. Next slide. Out on the campus there are plaques that tell about what has taken place in the buildings. If somebody like the 2 gentlemen at Animal Husbandry that made the blue cheese, there is a plaque that shows you the blue cheese. Here is a large round plaque that shows and Virtual Banner invented a large round baler. Next slide. Oh yeah, the alumni. Okay, this is a new slide on here. The alumni office has a inventor's corner, and let's see, where is that? There it is there. There's the round baler there. If you go out to the alumni office, you'll see the round baler slide, you'll see the blue cheese slide, you'll see the watermelon slide, and so forth. So we have had some creative professors out there. What's interesting about this is that there are 2 ag engineering professors, and their graduate students are mentioned in both of these different exhibitions. Okay, now I talked about the compactor, so we will go ahead next thing. And here is the compacting the soil. After the hay dries, compact this all into a smaller bale, just like the cotton people have been doing for 200 years, compressing the cotton in the bale. And so here is a large round bale compressor that was designed by this student night junior, senior design team. And they designed this so that you can use hydraulic pressure and you can condense the distance here and you put pressure on the bale and compact the bale for shipping overseas. You can ship those bales to Alaska, you can ship them to Japan, you can ship them to China. And so this is neat. They're looking about the future, but this is something that needs to go. Next slide. Here is round bale art. People from all over the world send me pictures of large bale art. And it's fun to see, and it's fun to see farmers using their creativity to build things that you can see from the highway. Next slide. Okay, this is the last thing that developed. It was the stripping of leaves of the alfalfa plant. Now, cows have been leaf strippers for millions of years. They only have teeth on either the bottom jaw or the top of the jaw. I can't remember, maybe sometime on the top. But I remember they had only one batch of teeth. And they strip the alfalfa plant when you have them harvest alfalfa plants. And so I decided that we should strip the leaves off the plant because they are very valuable. And so we did this, and it was very successful. So here we are in the procedure. We harvest 6 crops of leaves, and you get the same amount of leaves as you would get from 3 harvests of the whole plants. These leaves are worth about $400, $500, $600 a ton. These leaves here might be, if they're on the stems, might be worth $100, $150 a ton. Last winter it got up to about $250. A lot of money last year was spent on building Mayan hay last winter by the farmers. And and then in the last stripping, you take the stems off and you feed them to cows. Because what we found is that the alfalfa stems build another set of leaves. They grow another set of leaves. They've been doing it for millions of years, even. Here is the alfalfa stripper. We have it here, the elevator here that carries it back. And then the leaves go here in the box. Next slide. Here is the elevator running backwards to carry the heads of the plants underneath and into the stripping rolls. And then you can strip off the leaves. Here are the stripping rolls of a alfalfa compactor that they use to compact squeeze the leaves, the stems of the alfalfa plant. And so we converted it to a stripper. And here is a plot of alfalfa that has been stripped of leaves with a stripper. Next slide. Here it is alfalfa before it's stripped, and here is alfalfa after it's stripped. It looks like it has been grazed by cattle because they have lost its leaves. Next slide. Oh, and then I should say, then it grows another set of leaves, and then you can strip again, and we got 6 strippers. And here's George Harris on a tractor, and he's stripping leaves. He's carrying these leaves to a dryer over at eastern Iowa, and then, next slide, here is the leaves that we stripped, those were fed to pullets, a full ration of alfalfa leaves of red, and they did great. And this is something that they wanted to do because alfalfa was cheaper than some of the other sources of protein that you can feed animals. Next slide. I've had the job of trying to increase the use of the combine. The combine sits idle about 350 days a year. So here is a combine crushing alfalfa plants. And we crush the plants in order to smash the stems so it dries faster. And so here we are using a combine as a plant crusher. And it worked very well, except the industry doesn't like to have multiple uses of the machine, but Wesley Buchele does. And so what we have here is a new use for combines. Some farmers out in Montana actually built combines in distributors. Now, into crushers to crush the stems of the alfalfa plants. And next slide. Now, here is a parable with plow. Farmers want to plow faster, but if you plow faster, it takes more load and more gas to plow faster. And so, there, what do you do? Well, Kinsey-Ball built a variable width plow so that he could, when it was sandy soil, he could extend the width of the plow and plow the land. And when it was loam, he would condense it to plow a narrow field. But that made the road wavy as you went down through the field. And the farmers didn't like that, but the farmers liked the plow, and so they bought them, and John Deere and International Harvester and Oliver all built variable width plows. Well, Kinsey-Ball sued them and in court. Bob Tweedy, who was chief engineer of research, an Iowa State University student, called me up and said, Buchele, can you build a high-speed plow? I said, sure, I can design that. Well, what would it cost to build and develop a high-speed plow? And off the top of my head, I said $15,000. He said, I am writing a check. So he did write a check, he did send a plow, he did send a plow, bottoms, and he sent a plow, and he sent a tractor down here. Jim Adet took the plow to Arkansas, to Alabama, to the National Tillage Laboratory, tested it at various speeds and different approach angles, and then he sent it back, and Wainwright from England came and built it into a high-speed plow. And now farmers can go out in the field if they wanted to with a high-speed plow, and you can plow 8 miles an hour, or you can plow 2 miles an hour. It doesn't, what it turns out is that the approach angle has to be changed because as you increase the speed of the plow, you increase the throwing ability, and on 80 miles an hour, you'd be throwing the fur over the fence. Well, that kind of is my story. That's the story, the Wesley Buchele story that you said you would tell them. I've tried, and I hope I've done it. It's been a real pleasure to speak to you. I hope these all are comfortable being at home in Ames, Iowa, as the home of the inventions. Thank you very much.
Thank you so much for sitting still for the long story, the long short story of all of these inventions. And you know, we had to cut out a whole bunch of things because we just didn't want to keep you here all night. But Wes is willing to take a few questions. Is there anybody with a question specifically about anything? Hi, Danny. Go ahead.
How did you determine the optimum size of?
Go ahead.
How did you determine the optimum size of the large round bale?
How did you determine this optimum size of the large round baler?
I don't know, you can make it any size you want to, but it's always nice to start out small, because it's easier to work with something small than it is large. And it seemed like we kind of settled on 5 feet wide, and that's where they are today.
So 5 feet was small? Yeah, okay, so it could be bigger. Could have been bigger as well as smaller. Any other questions? I can't see. Oh, there you go. Hi.
Thanks, Les. Did your twin brother amount to anything?
Did your twin brother amount to anything?
Oh, yes, he did. He became the General Secretary of the Inter-Co-op Council of the students who were living in cooperative houses at the University of Michigan. When he went there in the early 60s, they had 5 houses. When he finished, they had 17 houses. He did a great job of helping a lot of Michigan students get an education at the University of Michigan. And he was honored as the Farm Cooperative Hall of Fame.
Are you familiar with cooperative houses? It was a way to go to school and have a little more economical housing situation. Other questions? Yeah.
In the 50s, I.S.U had a small round baler. Were you able to use any of their principles in your development?
He said in the 50s, I.S.U had a small round baler. What was the rest of the question?
Was he able to use any of their principles or any of their techniques?
Did you use any of their technology?
Well, I.S.U did study the Lebanese baler that was invented in Nebraska in 1892 and then was eventually made into a self-propelled unit. And it had a problem in that when you turned the baler out baling and if you started to tie a bale, you run out of hay to carry the twine to the bale so that the bale would pull the twine and have the twine actually up in the bale. And so I.S.U had to quit manufacturing because they couldn't keep farmers from trying to take a batch of hay and catch that end of that twine and get it caught in the rotating bale, because when they caught it in the rotating bale, they grabbed their arm and pulled off their arm, and they were suffering a lot of court battles, and so they quit that. In 1961. In fact, that was the thing that caused me to think about the round baler, because we needed a round baler that was weather resistant. And so it wasn't until '65 that I actually proposed the round baler to Virgil Haverty. But in the meantime, Vermeer in 1970, 69, 70, the story is that he was going over his farm, the farmer's farm, a friend, and the farmer said that he was going to quit raising cattle because of the tremendous amount of feeding bales of hay. Well, first making hay in the fall when you couldn't find anybody to come out in the field and help you, and then feeding the hay throughout the winter to the cattle. And so he was going to quit producing hay, producing cattle and producing hay. And so what that Vermeer took that as a challenge, and he did study the Evans baler, but it had that problem, and he decided that it should be bigger, and Hawkville was already building a bigger baler. Hawkville was building a bigger baler over Benton, so he decided to go out in his machinery shed and he put 2 sawhorses here and put 2 plywood boards, 4 by 8 plywood boards on the lot, and he drew the nails, and then he put a string to the nail and a pencil and drew a round baler 6 foot in diameter. And then he worked out the work on it. He had already studied the round baler, the baler that Evans made, but it had that problem, and he wanted to get rid of that problem, but actually he ended up with another problem that killed a lot of farmers in the meantime. But anyhow, that has been solved by another inventor here in Iowa. I'm not going to ever come up with his name. But anyhow, the tractor, the balers are safe now. At one time, they were very dangerous. But Vermeer has made a name for himself of building machines that nobody else would build. And they build so many different machines, and they just do a wonderful job.
Other questions? Yeah.
You didn't tell us about filling up the solid waste plant with corn stalks.
He said you didn't tell us about filling up the solid waste plant with corn stalks. Over here in Ames, burning. Has anyone, are you implying burning?
They were for burning, yeah.
For burning. Has anyone ever harvested corn stalks to burn for fuel?
Well, I had a project with General Motors in 1975 to harvest corn stalks, bring them into the Buick plant, and feed them into the boiler of that plant with coal to make Buick cars. And I was doing research. In fact, the other day, as I was looking around, I found my third report. And it was very good. And people today would like to see it. But what happened was that Buick vice president was elevated to some other post. They brought in a new vice president. He looked at the work they was doing there, and he said, "What are we doing harvesting corn stalks? We're building Buick cars. Let somebody else harvest those stalks."
And we promised you at the beginning that we would have a door prize drawing. Here she comes now. And I just want to remind you that if you would like the fascinating, longer story of a number of Wes's inventions, he brought a number of papers, and they are out in the shop in the lobby. So you can really indulge in a lot more information if you want it. Wes, we're going to let you do the drawing here.
I didn't put anything in.
Oh. Wes, you have already won. See, that's the thing. Okay, I'm going to mix that up. You need to draw two names. Two out. Okay, there's one. Linda White. Woo! And Jean Humphrey. She's still here? Still here? You need to report out to the shop in the lobby, and they will provide you with your wonderful prize. I did mention the books. The book, now you know that Wes is a twin. He and his brother Luther wrote a little history of or a little memoir of their growing up years with their older brothers, with that hassle of older brothers. And that is in the lobby as well. The next lecture is April 22nd. We're going to be talking about collegiate manufacturing. Teresa Larson will show her wonderful film, and then we'll talk more about some of the episodes that she was not able to include in the film, so it will be an expanded evening of memories about collegiate manufacturing. April 22nd, 7 p.m., right here. Wes, we thank you. What a fabulous time. So if you have any other questions, please feel free to come up and address them to Wes directly.